Hello everyone, and welcome to this second spatial interpolation method about kriging. Let me introduce myself. My name is Ken Arroyo Hori, and I'm another lecturer for the course. I'm a researcher in the same 3D information group as Hugo. So let's get started with today's topic. The idea of today's lesson is to do two things. First of all, to give you a bit of an overview, a theoretical overview about kriging, and then to show you a bit how you can perform kriging in practice using a Python library that's called PyInterpolate. Let's get started with the theory first. So let's discuss a bit what is kriging. So kriging, in short, is a weighted average interpolation method, similar to many others that you have seen throughout this course. However, the weights here are based on the spatial correlation between the points. How do you compute this spatial correlation? You create a custom geostatistical model for each dataset, and in order to do so, you use a tool that's called a variogram. We will go through each of these steps, so don't worry if you don't understand everything yet. Let's start by looking at one dataset here. So this is an elevation dataset, and you can tell that there's sort of a hill somewhere here in the middle, right? So there's an area of higher elevation in the middle that tapers off towards the side, towards areas with a lower elevation. Using a dataset like this, you can perform kriging to be able to interpolate points anywhere in this domain. In order to do so, the first step is to create what is called a variogram. So if you just take any of the points in the original dataset, you will notice that for every pair of points, let's say these 2 points, there's a certain distance between them, and there's a difference in elevation between them. So if you plot these two values using the x-axis for the distance and the y-axis for the difference in elevation, for every single possible pair of points, or for a representative subset, you end up with what is shown here on the left, which is called the variogram cloud. And you will notice already here some interesting patterns, right? So when you start at the very beginning on the left, you will notice that points that are very close together tends to have very similar values. And as you move towards the right, you will notice that as you move to points that are farther apart, these can have more different values. So there's already something of a pattern emerging, but it is not very clear yet. So yeah, if you see what happens here on the right, the idea is that in order to create the experimental variogram, you create a bin. So you basically do averages over certain intervals. And here the pattern is very, very clear already. So at the beginning, points that are very close together have very similar values. And as you move to points that are farther away from each other, they have more different values. So using this experimental variogram, which you created using the input data, you can move on to the next step, which is to create a theoretical model. So in order to create a geostatistical model using what we have seen before, the idea is that you can already see certain parameters in the curve that you just saw. And the 3 typical ones that are used in order to create the model are called the seal, the nugget, and the range. So the seal is basically the maximum difference that you can find, the similarity between values even as you reach a point. So in other words, there's a certain distance at which there's basically no spatial correlation between the points. So the seal tells you what is the maximum dissimilarity there. The range tells you what is the distance that you need to get to in order to reach the place where there's no spatial correlation anymore. And then there's the nugget. So the nugget is kind of the point where you do an intersection with the y-axis, and it basically tells you something related to how much noise there is or how much error with the measurements, because even points that are very, very close together will have a certain dissimilarity. So that is the nugget, and using the seal, the nugget, and the range, we can create a few different functions. These are the three typical parameters, as I said. But using these three different parameters, you can fit many kinds of different functions. Here I'm showing a certain sample of them. Yeah, in this case, there's a circular model, a cubic model, an exponential model, Gaussian, linear, bounded, and power bounded models. And you can see the details of each of these and the formulas to calculate them in the terrain book. But roughly you can tell that the Gaussian model here has a very good fit, so it matches very, very close to the values of the points of the dissimilarities, whereas some of the others don't do nearly as well. And these will differ depending on the dataset and the characteristics of the dataset that you are using. So as I said before, kriging is a weighted average method. So this is the typical formula for any kind of weighted average method. You do sum over all of the points. Each point is assigned a certain weight, as in the weighted average. And it's you sort of divide it by the sum of the weights. This is kind of a way to normalize it so that the total sum of the weights is 1. So where does this come in terms of kriging? So let's say that we want to do certain interpolation. We want to interpolate what is the value at x using these 3 different points, one which is 5 meters away, one which is 19 meters away, and one which is 15 meters away. The idea is that the points that are closer together will have a stronger spatial correlation than points that are farther away. So the weights that are given here on the right will be basically determined by the different distances, and the exact way in which you do that depends on the kind of kriging method that you're using, but basically you can use the variogram to figure out what is the spatial correlation between the points at different distances, and it will provide you with different weights. The details for the different methods are in the terrain book, so you can check that there. But before we move on to the practical part, let's summarize a bit what makes kriging special, so what is different with respect to other methods. So kriging models the correlation based on the specific characteristics of each dataset. You don't intuitively just assign a value like with a IDW, let's say. You use the specific spatial correlation at different distances in a dataset to figure out what is the spatial correlation there. Kriging mathematically minimizes the interpolation method in a few different ways depending on the kriging method, and it's able to handle complex data with many kinds of different characteristics. You can have noise, which is handled using the nugget effect that you saw. It can handle irregular point spacing because you can really figure out what is the spatial correlation for points at different distances. And it can handle also regular patterns well, because whenever you set up something like a threshold for the maximum distance, you end up with artifacts with using other methods. So that makes kriging a little bit special from distinguishes it from some of the other methods that you have seen in this course. So using what we have seen before, you can create a geostatistical model. And even though this depends on the specific type of kriging that you're using, roughly kriging tries to model 2 different things. It tries to model an expectation and a residual. So the expectation is sort of the big trend that you can see throughout a certain data set. And the residual kind of models the deviation from that trend. So what is the local variation? The expectation does like the global variation, what is the big pattern, and the residual shows the local variation, so the small differences in a particular area. In this lesson, we are looking at two different types of kriging, simple kriging and ordinary kriging, and these differ in how they handle the expectation. So simple kriging assumes that the expectation is a known value. Many times you can do a guess, although many times you really cannot, and it's not ideal. And for ordinary kriging, you kind of compute a local mean as you go, which means the method is a little bit more complex, but it's also more applicable to other datasets. Which one performs better depends on the specific dataset, although ordinary kriging tends to perform better than simple kriging. So now let's have a look at how you can perform kriging in practice using a Python library that's called PyInterpolate. So what is PyInterpolate? Basically, it's a Python library for geostatistics. It's focused on a few different interpolation methods, mostly on kriging. You can do IDW, you can use simple kriging, and ordinary kriging, among others, and you can perform different operations on baryogram using this library. You can create things that we will not cover in this lesson, like directional baryograms, and you can also use the tutorials to learn more about how you can perform kriging. I will go through some of the tutorials for this that are available in the PyInterpolate website in pyinterpolate.readthedocs.io. So let's have a look there. So if you go to the PyInterpolate website, you reach this place. It has like a small description of what the library does, and if you go to setup, you can see how you can install it using both conda and pip. But for this lesson, I want to go through two of the tutorials. One from the beginner section on how you can estimate baryograms, and one from the intermediate section on how you can perform ordinary kriging and simple kriging. There are several others that might be interesting if you want to have a look, like semi-baryogram models really shows you how you can do comparisons between how different functions fit. But yeah, the basics are covered in these two. So let's have a look at the semi-baryogram estimation tutorial. You have a nice description of what the method is doing, and most importantly, you also have the code. So basically, you can just take this code, copy and paste it and run it directly. This is already using some of the sample code that's available already in the same repository as PyInterpolate. And I think it's in particular using a specific dataset about Poland. So in order to use PyInterpolate, you need to use NumPy. So you need to import NumPy, and preferably you also need to use matplotlib. Like matplotlib is used to in order to show things like the baryogram, in order to see which function fits best. PyInterpolate has some functions to do the automatic fitting for you, but if you want to do it interactively, you basically need to use matplotlib. From PyInterpolate, you are going to use a few different things from this tutorial. readTXT just reads a simple text dataset. This function to build an experimental baryogram does what it says. You can also use, you can plot it from there. And similarly, there are a class and a function to create a theoretical baryogram. So first of all, you can use this read data function, readTXT, in order to read a dataset. Here it's showing you a few different lines from the dataset, and once you have read it into memory, you can create experimental baryogram using the functions available. Basically, you can look at the function here, which tells you what dataset you need to read, what is going to be the step size, so the bin size for the baryogram, and what is the maximum range. As we discussed a bit in the terrain book, something like half the size of the maximum distance between points is usually appropriate, but it differs a bit depending on the dataset. And once you create the experimental diagram based on this, you can actually output it, and it creates a table that like this. Usually we want to have a look at the string variance, and you can tell that as you go to points that are further away from each other, the same variance grows. And you can use this plot function inside the experimental diagram in order to show what is the pattern there, so how quickly it is growing. Then in section 3 you can set manually some different diagram models. This is the theoretical diagram function that we saw in the theory and in the book. There you can define the seal, the nugget, and the range manually, and you can put this into the build theoretical diagram function. This is kind of the manual way to do it. So you first do a plot like we saw before. You define the 3 different values based on what you see. You build a theoretical diagram function. You can tell here that it is using a circular model here in this part about the model name, and PyInterpolate has support for different models like circular, cubic, exponential, Gaussian, linear, power, and spherical. And you can try all of them, see which one fits best. It's kind of a recursive process where you build a theoretical diagram using the different parameters. You plot it like this, also using the plot function inside the model that you just created. And you can adjust the 3 different parameters based on what you can see. So for each of the different models, you can adjust, plot, adjust, plot, adjust, plot until you get as good a fit as possible for the model. You try different models, and that's how you end up with what you choose. That is one option. So in this tutorial, it goes through a few different models like the circular model, cubic model, exponential model, and so on. This is trying to automate a computation of the error, different models. So like for the circular model, the root mean square error is like 63, for the cubic one it's like 100, and so on. I think this could be optimized because usually the seal, the nugget, and the range are not exactly the same for different models, and in this tutorial it's using the same value for all of them. But yeah, it's one possible approach, and the idea is that you can also get a measure of the error, so you can do things not only visually, but also you can get a number behind it and see which model fits best. Then the other approach is to try to use the functions available in PyInterpolate to automatically set a model. For this, there's an autofit method that tries to do different models with different parameters. But at the end, the important thing is that as you run the autofit function that is available here, it figures out that the best fit is with a linear model. And it gives you some details about what the nugget, the seal, and the range are for this automatically fitted model. If you really try to fit it manually, using different models, doing it recursively, well, iteratively with different parameters, I think you're going to get a better fit. But this is going to be a reasonable approach in order to test many different models, many different parameters. Also, if you want to fully automate the process. Yeah, so basically for the given dataset, this is the best fit that was automatically fitted. There's a bit of a red flag here in the sense that the dissimilarity tends to increase and increase and increase, and it's never really flattening at any point. So I think usually you need to kind of use a bigger range and plot it in order to see whether it really tapers off at any point or not. Interesting thing here is that you can also export or import the model using functions available in PyInterpolate. So once you have figured out which is the best model, you can just export it to a file, and you don't need to rerun this whole thing about figuring out the baryogram, fitting, and so on, because this can really slow down the process. So once you do this first step, you export the model, and then you can just write it to a file, and you do the second part, so the actual interpolation, using a model that you have imported because you have created it before. Yeah, so now let's have a look at the second tutorial. So how can you perform ordinary kriging and simple kriging using PyInterpolate? For this, it's using the same dataset that we saw before. So the tutorial is just reading the dataset, and it's creating a function here that does training and testing for this. It says the baryogram model. Here you can see the step and the range. The dataset is plotted. The theoretical baryogram function is shown here, so it's the linear function, maybe a different one, slightly from what we saw before. And yeah, so this is the part where the second tutorial really differs from the first one. So this is how you set the different models for ordinary kriging and simple kriging. The key thing for PyInterpolate is that you can use this kriging function, and you actually tell it to do simple kriging or ordinary kriging by passing a certain parameter that is shown here. You need to pass it some other things, like the theoretical baryogram model that you created in the previous tutorial or in the previous part of this tutorial. Yeah, the other parameters are kind of self-explanatory, but the key thing is maybe that if you use simple kriging, you need to have a known mean, as we have said before, so you need to actually give it to the kriging function. Whereas with ordinary kriging, it will try to do kind of a local mean and figure it out on its own. In this tutorial, it tries to do something that is pretty typical for this kind of approach. So it divides the dataset into two parts. There's a training dataset and a testing dataset, which are subsets from the original. So you want to use the training dataset in order to create your model, and you do interpolation at the points that are available in the testing dataset and figure out what is the error between the interpolated value at those points and the actual value in the dataset at those points. By doing so, you get a sense of how well the kriging method is working out in practice. And if you do this interactively, it will actually tell you how many iterations it's able to do per second. So you can optimize this a bit using the other parameters, like the number of workers available for kriging and so on. Yeah, so indeed, the tutorial here is trying to predict the value then at unknown locations. So this is giving you the root mean square error depending on how many neighbors it's using. The idea of using only a certain number of neighbors of the point to be interpolated is that you want to make the method faster. So you can tell that when we were only using like 4, 8, or 16 neighbors, we were able to do like over 3,000 iterations per second, but as you get to more and more neighbors, the iterations drop like from 3,000 to like 200 to less than 100 or around 100, and you don't gain really much in terms of the error, right? So basically you want to figure out what the best parameters are in order to get good fit, but also good performance for your method. The tutorial does this for ordinary kriging, and it also does it for simple kriging. In theory, you should be able to see lower root mean square error for ordinary kriging in most cases, but yeah, not always. So this will really differ depending on the dataset. This is an interesting small bit from the tutorial. So if you want to do some things that are a little bit more advanced than these two tutorials, these are some interesting other ones. So you can do benchmarking for different types of kriging, so which one performs better than others. You can tell how to deal with outliers, which is kind of important in these kinds of datasets. You can do directional kriging, so maybe the variance or the spatial correlation is different depending on the direction that you're looking at. And then there are some tutorials about how you can do kriging with areas and other more advanced topics. Yeah, so basically this has been it for the second spatial interpolation method about lesson about kriging. I will be answering questions also on the Discord, and feel free to contact me if you want any more information about this topic. All right, thank you.